Welcome back, AP Calculus AB, to your AP Targeted Review. This video is for AP Calculus AB students only. There is a BC version of this video in the BC playlist, so don't get confused. If you're AB and you've picked the wrong video, you will notice by the time you get to some methods that you've never heard of before, and if you're BC, you shouldn't be in this video. Go to the other one. All right, what are we doing today? We are looking at differential equations and slope fields. We need to remember that differential equations are just defined as any equation that has any sort of derivative, whether it's the first derivative, second derivative, so on and so forth. It can combine multiple different levels of derivatives. However, we're really just going to deal with first order differential equations, which are differential equations that have a first derivative in them. As always, we will come back to the bullet points at the beginning of this once we've finished the free responses so that we can kind of summarize and you guys can decide which are the most important concepts that you need to remember. So let's get to it. We only have, I think, maybe 2 free responses today, 2016 and then 2017. I have adapted them though, so I've added a couple extra pieces in there just to make sure we get kind of a full rounded view of everything. As always, you should try to work this ahead of time so that you're not just sitting here listening to me drone on. You want to work it, and then if you get stuck on anything, go back and watch those specific parts. So go ahead, try 2016, and then we will run through it after. Ready? Set, go. All right. Well, part A has us sketch a slope field. You should be super happy if there's a slope field problem. They are easy points, usually between 1 and 2 points on a free response. We have a differential equation right here. It has a derivative. It tells us the first derivative is equal to y squared divided by x minus 1. So let's get to it. We need to find the slopes for all 6 of these points. A few things I like to look at first for this derivative are, where are the slopes 0? I find that is a little bit quick. So for example, when y is 0, it turns the whole fraction to 0. So those are points that are something comma 0. Where are those points on our graph over here? Well, I think these 2 points fit that, right? This is 0, comma 0. It has a slope of 0, and 2, comma 0 has a slope of 0. You might notice there's a big gap in the middle right here, and that I think is because of this x minus 1, right? What would cause x minus 1 to become 0? X minus 1 to become 0 happens when x is 1. So that's any point that's in the form of 1 comma something. And what happens if the denominator of a fraction becomes 0? Well, then you're dividing by 0, which is a big no-no. It's undefined. It could be infinity, negative infinity. Either way, we just say undefined slope. And on a slope field, they will never have you sketch the slope. They will never have you sketch the slopes that are undefined. So there would never be points here, because then the argument is, well, wait, does the line go straight up and down? Or if no slope exists, shouldn't there just be nothing there? So they always leave those blank. That's why there is nothing at 1 comma 0, 1 comma 1, 1 comma 2. All right, I think that just leaves us with 4 more. So let's work our way up. This is the point 0 comma 1 right here. So I'm just going to evaluate dy dx at 0 comma 1, or of 0 comma 1. Y is 1, x is 0. You do not need to show this. I imagine most people would probably just do this in their heads. We get 1 over negative 1, so that's a slope of down 1 over 1. Right, negative 1. So if we're thinking here and you're thinking of a slope of down 1 over 1, then I'm just going to make sure that my little slope line just points at approximately down 1 over 1. Okay. What about this guy over here? We'll change colors again. This is the slope 2 comma 1. So if I do 2 comma 1, can you see it? We have 1 squared over 2 minus 1. I think that just becomes 1 over 1, which is just up 1 over 1. So it looks pretty much exactly like the yellow one, just pointing in a separate direction. All right, as we continue on, this is the point 0 comma 2. So if we evaluate dy dx at 0 comma 2, we get 2 squared over 0 minus 1. That looks to me to be negative 4. So negative 1, 2, 3, 4 over 1, pretty steep, something like that. And then if we look at our very last one over here, this one in black, I guess, haven't used that yet, we have the point 2 comma 2. So dy dx evaluated, sometimes you'll see it like this, at 2 comma 2 is 2 squared over 2 minus 1, which is positive 4. And so we have up 1, 2, 3, 4 over 1, so something like that. All right. There is a second part to this. It says, define the portion of the graph, so explain the portion of the graph which contains only negative slopes. Well, you can notice over here, these are positive slopes or 0. These ones are negative. But when they say the portion of the graph, they don't mean just these two. Because, for example, if I had picked a point in between 1 and 2, that would also have a negative slope. I believe this point up here would as well, and probably this one over here. So they're saying graphs have an infinite number of points. Which ones have negative slopes? Well, to do that, let's take a look at the equation for our slope, or our first derivative, and let's say, well, we're trying to determine when dy dx is negative, or less than 0. And we know dy dx is defined as y squared divided by x minus 1. Okay, so really, if we just analyze this, it becomes, what would cause this fraction to become negative? Well, certainly the top, I think, is irrelevant. The top is always positive, isn't it? When you square something, so that can't contribute to negatives. So I think it's just got to be the denominator. If x minus 1 becomes a negative number, then all the slopes are negative. So if we add 1 to each side, I think anytime x is less than 1, you will have negative slopes. And I'm just going to state that in a quick sentence. So when the x coordinate is less than 1, the slopes are negative. All right, let's move on to part B. Let y equals f of x be the particular solution to the given differential equation. Now, this phrase is kind of that buzzword phrase where if you see it, you should really key in and say, ooh, I think this is the one that's worth lots and lots of points. Because ultimately what would happen is they would ask you to try and solve this differential equation so that you only have x and y, and you can figure out the original equation whose derivative or derivatives match the differential equation there. However, as you carry on, it says, write an equation for the line tangent to the graph of y equals f of x at x equals 2, and use your equation to approximate f of 2.1. So what's going on? Well, I'm going to erase this part, so be ready for it. They're saying we have some original equation that passes through the point 2, 3. Let's say it does, I don't know, something like that. Great. I don't like that. It does something like that. Cool. They're saying we want to know the value at 2.1. We are interested in whatever this y value is. 2.1 comma what? And this is our equation, y equals f of x. However, we don't have this equation. We are not going to find it in part B. Instead, we're going to write a tangent line that passes through this point right here. And I wish that had switched colors, but oh well. Second try. There we go. So you're going to write a tangent line which passes through the point 2, 3. And then you're going to use that tangent line to evaluate the point 2.1 comma something. And we're going to hope that these somethings are pretty close together, right? That's the nice part about tangent lines, is they are pretty close to the original graph, so we're going to use a tangent line instead of the original graph. All right, so how do we do that? Well, we write a tangent line. So I used yellow. Let's continue. So my tangent line is going to be f. Now I could write f prime of the x value. I'm going to alter that in just a second. X minus 2 plus, and I'll keep it as f of 2. There are two things, though, that I want to change here. First, this is at the point 2 comma something. A lot of times I see students say, ooh, 2.1, let's put in 2.1. We do that at the end. And second, I'm not going to write f prime of 2 because to me that means a function where you only have one input. But if you look at our f prime or our derivative function, there are two inputs, x and y. So I actually prefer to switch this up, and I'm going to say we're going to write dy dx at the point 2, 3. Okay, so let's go ahead and evaluate this out. Have we done 2, 3 yet? We have not. Unfortunately, it was not on our original slope field, so I'm just going to do the math down below. So dy dx evaluated at 2, 3 will be the y value squared over the x value minus 1. So that looks to me like 9. And so I think our tangent line then will be 9 times x minus 2 plus f of 2, which is 3. There's my tangent line, nothing bad. But then we've written the equation for this line. We need to figure out what is the y value that's over here, the y value at 2.1. So they said we want you to find f of 2.1, the one that I've done in blue here, but we're not going to be able to do that. So instead, we're going to use the tangent line and find 2.1. So f of 2.1 is going to be evaluated using my tangent function, 9 times 2.1 minus 2 plus 3. And I am not going to simplify that. That's it. We're done. All right, moving on to part C. Now notice it really has a very similar setup to B, where B said let y equals f of x be the particular solution. Now C says find the particular solution. And this is, and I'm going to star this problem, this is the one that you never skip on the differential equations section. There is almost always a differential equation, almost always, on the free response, where it's going to say find the particular solution in this form where y is isolated, the output is isolated, and it's usually worth between 4 and 6 points. Remember, a free response is worth 9 points. My guess is this free response would have probably been worth a point for this, maybe a point for this here, so there's 2 points. 3 and 4, or maybe just 1 point, but we'll say 4 points there, which means that if this is the last one, this has to be 5 points because there are 9 total points in a free response. This is worth more than 50% of your score on this free response. Don't skip this problem. If you're like, but what if I don't know how to do it? Then you need to spend the next couple weeks before the AP exam practicing more of these. You need to be so confident on the process. So what is the process? Well, there's really 5 steps. I always divide my paper into thirds. The first step is you start with your equation. Looks something like this. And you separate the variables. This type of differential equation is known as a separable differential equation because you can separate the variables. You are able to, using only multiplication and division, move all of the outputs to one side, the inputs to the other. The dx is being divided by, I need to multiply the dx over to the right side, like so. And then I really don't want the y squared here, so I'm going to divide that or multiply by 1 over y squared to the left side, and 1 is a placeholder. All right, that's worth a point. Just knowing how to separate the variables like that usually takes 1, maybe 2 algebraic steps, 1 point down. The second and sometimes third points come from actually integrating this. So I always like to slip the integral symbol in once we've separated the variables, and then I'm going to rewrite this to make this a little easier. Y to the second power, y to any power except for 1 in the denominator, tells me I'll need to move it up to the numerator. This one, though, is x to the first power, so I will actually keep that in the denominator. What is our antiderivative? Well, we add 1 to the power, y to the negative first, and we put an extra negative 1 out front, equals, and then this is going to be natural log absolute value x minus 1. Don't forget the plus c. Moving on, we actually need to determine the plus c, so we'll use that initial condition over here, which is an input of 2 and output of 3. I'm going to rewrite this y to the negative first as negative 1 over y to the first equals natural log of something minus 1 plus c. Output input, negative 1/3 equals natural log. 2 minus 1 is 1. The absolute value of 1 stays 1 plus c. And you can just move your natural log of 1 over to the left side and be done. However, I would encourage you to know something about the natural log of 1, or any log of 1, and that is always 0. And so we find c is negative 1/3. Okay, what's the last step? Well, the last step is we need to make sure that this equation is written in the form of y equals the stuff happening to x, which means the output variable is isolated, and currently y is not isolated. So negative 1 over y, I'm just moving this piece to the denominator, equals natural log absolute value x minus 1 minus 1/3. That's the c value. We need to isolate y. I'm going to get rid of the negative first. That seems like a not too terrible first step, right? And then, and this is kind of the tricky part, it's like, well, how do we get rid of this 1 over y? My favorite way to do this is to realize that if we flipped this fraction over, it would be y over 1, which is really just y. So why don't we just flip or reciprocate each side, which you're allowed to do, as long as both sides are written as a single term and a fraction. These are two different terms, but it's very easy to write that as a fraction. Just replace the whole thing or put the whole thing over 1. So what is the reciprocal of that? 1 over negative natural log absolute value x minus 1 plus 1/3. And we're done. 5 points here. 1 point, 2 and sometimes 3 points, 4 points, 5 points. You need to practice it. It's a really easy way to boost up that score. Okay, the second and last problem that we're going to go through today is one that you have done before, maybe even more than once, but I think it does a really nice job highlighting several different issues that can potentially arise on free responses. This is our friendly boiled potato problem from 2017. It was the memed problem for the year. Usually, since there are 6 free responses, students tend to latch on to one of them and say, oh, hated how they did this one, we're going to write memes about that. Sometimes more than one, but it's usually one problem that shows up on Twitter and memes and all that fun stuff. So this was the one from 2017. Students did not like the boiled potato problem. My students did very poorly on this, and so I've taken to teaching it better since then. Let's get to it. The internal temperature of a potato is 91 degrees Celsius at time t equals 0. And the internal temperature of the potato is always greater than 27 degrees. 27 degrees is not picked arbitrarily. It's 27 degrees because that's usually a good estimate for indoor room temperature. So essentially, the potato starts at 91 degrees, close to boiling water temperature, and is cooling down until the low point that it'll hit is room temperature, or 27 degrees. It'd be weird if it dropped under room temperature. Then it'd be like sucking heat in. I don't know, it'd be a very strange potato that way. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies that differential equation, dH dt blah, where h of t is measured in degrees Celsius. I like to think h stands for heat of the potato, and h of 0 equals 91. Part A. Write an equation, it says from, it should say for, the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature at t equals 3. Okay, tangent line, we've done that before. We're not going to use t in our tangent line, though, to name it, though, because they're using t as our variable. If I can't use t, my fallback is usually to use the letter L, where L is like a linear approximation. It's a line. So I'm going to say L of t is equal to, and I'm not going to use h prime. I'll use this notation over here, is equal to dH dt evaluated at, well, and this is kind of strange. There's only one input here. So if there's only one input, we might want to think about what the input is, right? In particular, we know that h of 0 equals 91. So maybe I'll just write this as 0, 91, and then we'll come back to that. T minus 0 plus 91. Okay, so then we have to evaluate dH dt at 0, 91. So dH dt evaluated at 0, 91, and so we have this cool formula over here, negative 1/4 times something minus 27. And here's the first part that my students definitely made mistakes on a couple years ago. They weren't sure if you're supposed to substitute in 0 or 91 for h. This function notation threw them for a loop. But, okay, we know that this is h of t, where t is the input and h is the output. And we should be comfortable with function notation to know that 0 is the input, which means 0 is the time, and 91 is the output, which is the heat of the potato. And they tell us that in the problem too. So 0, 91, what replaces the h here? Well, the 91 replaces the h, not the 0. If you had substituted in 0 there, you'd get a negative times a negative, which is a positive, which would tell us, because this is all about potatoes, it would tell us that the heat for the potato has a positive slope, which means the potato is increasing in heat. And that, again, would be a very strange potato if you pulled it out of the oven and it had a consistently positive slope. 91 makes a lot more sense. And although you could leave your answer here, if you were pressed on time, you could just rewrite this a bunch of times. I think it's probably easier to simplify this just a little bit. 91 minus 27, 64, and a fourth of that is negative 16, I think. Here we have a negative slope, which to me makes much more sense in context of the problem, right? The potato is decreasing in temperature. So, final linear approximation is going to be negative 16. T minus 0 is just T plus 91. Use this equation to approximate the internal temperature of the potato at a time of 3. So what are we doing here? Well, the internal temperature is the heat of the potato, so we're trying to find H of 3. But we don't have the equation for H, so we're going to do H of 3 will be approximated by my linear approximation at 3, which means that H of 3 is approximated by, switching colors again, negative 16 times 3 plus 91. And I'm not going to simplify here. I don't need to do anything else with that, so why bother to simplify? We're done. All right, part B. Use the second derivative to determine whether your answer in A is an under or overestimate of the internal temperature of the potato. Well, second derivative tells us about concavity of the original function. So concavity-wise, we either have a graph that's concave up or concave down. We wrote a tangent line, so let's say it was concave down or concave up. Tangent line-wise, notice if you compared these 2 points, the point on the tangent line is always below the point on the graph. So these tangents would be under approximations. Versus if you were concave down, comparing these points, the point on the tangent line is above the point on the graph, so the point on the tangent line is an over approximation. Really, what we need to do is determine, is our graph concave up or concave down? And to do that, we probably need to find the second derivative. So let's begin. We know that the first derivative is negative 1/4 times h minus 27. To get to the second derivative, we'll have to do ddt of each side. I never like when there's parentheses if they're easy enough to drop, so I'm going to go ahead and quickly redistribute that, or I guess just distribute that, negative 1/4 h plus 27/4, and then we're going to apply that ddt on each side. Probably should have left more space. Oh well. So d and d gives us that d squared h. dt times itself is dt squared. On the right side, negative 1/4. The derivative of h with respect to t is not 1, but rather dh dt. And then 27/4 is a constant, which is just 0. However, and you will see this on many of these types of questions, they won't want your second derivative, we say, in terms of the first derivative. They'll want your second derivative in terms of the original independent and dependent variable. So in terms, in this case, of h and t as specific variables. Now, they didn't say to do that here, but I find it's easier to do that. So what I'm going to do is say that the second derivative in terms of just t and h are negative 1/4 times, and then let's just take this original guy down here, negative 1/4 times h minus 27. And in fact, going one step further, let's just distribute the negative 1/4 right here to get positive 1/16 times h minus 27. All right, now we have a second derivative that's a little bit easier to analyze. So let's analyze it. We need to determine, is the second derivative positive or negative? But the issue is, depending on the value of h, it could be positive and it could be negative, right? If h was 0, 0 minus 27 is a negative value. But what do we know about h from this problem? I think it was a little subtle here, but didn't they tell us that the heat, they told us that the heat of the potato is always greater than 27 degrees. That means our value of h is always larger than 27. So if h is always larger than 27, can you see what's going to happen to the second derivative? Right? As d square h over dt squared is greater than 0, as h is greater than 27, then the answer in part A is, and then I never remember this, let's see, so second derivative is positive, it's concave up for the original graph, so then tangent line is an underestimate, is an underestimate estimate. There we go. You could go further and you could say the second derivative is greater than 0, which means h of t is concave up, which means the tangent line is below. But really, as long as you reference this and then underestimate, you should be good to go. All right, last page. I know we're already there. Very exciting. For t less than 10, an alternate model for the internal temperature of the potato is the function g that satisfies this different differential equation. Okay, find an expression for y equals g of t. Buzz phrase, find the expression for y equals g of t. That means we're solving this differential equation by working backwards, taking the antiderivative. And then, based on this model, what's the internal temperature of the potato at time t equals 3? So same thing before. Having done this problem, though, a few times, instead of splitting my paper into 3 parts, I'm going to split it into fourths. So I'll do half, and then here are my fourths as we go through. Still probably going to run out of room. This problem is a monstrosity. You shouldn't worry about running out of room on the actual AP exam. I seem to remember that this part C took up an entire page or entire piece of paper, so you've got plenty of room there. So don't stress. If you do need more room, you can always ask for paper and then staple it and attach it to your test. That's allowed too, but I don't think I've ever had a student need to do that. So let's get to it. Separation of variables first. dg dt equals negative g minus 27 to the 2/3 power. Well, when we separate these variables, I'm pretty darn confident that the dt definitely needs to go to the right side. So let's multiply that dt over there. I'm going to put an invisible -1 here, and I'm going to leave the -1 on the right side. I'm going to divide the g minus 27 to the 2/3 to the left side, and then keep the dg over here. Writing this -1 out front is a pretty nifty trick, especially if there's no other expression or term with t on the right side, and you're like, is it just dt? That seems weird, and it is weird, so I would put in either the invisible -1, or if you moved all of this and kept the negative here, you'd write a +1. I'm not a fan of moving an extra negative. Why make this antiderivative more difficult when you can make this one, which is already an easy antiderivative, slightly more challenging? Okay, then I slip in those antiderivative symbols. We're not doing the antiderivative yet, though, because I need to move this up to the numerator. Right? This isn't g to the first power, it's g to the 2/3. So we have the integral g minus 27 to the negative 2/3 dg equals the integral of -1 dt. Antiderivative time. Add 1 to the power. So g minus 27 stays the same. Adding a whole, 3/3 to -2/3 gets me +1/3. What goes in front to cancel out the 1/3? I think a 3. Equals. On the right side, I see two common mistakes that show up here. First, people say, ooh, derivative of -1 is 0. And you're right, but we want the antiderivative. Like, ooh, antiderivative of -1, that's -x with a plus c. And you're not wrong, but this is with respect to t, so it's not going to be -x, it'll be -t here. And I think that's about as far as we need to go for the first one. Next part, we need to use our initial condition. G of 0 is 91. So, it might help you just to see this. Don't forget that the 1/3 power is the cube root of g minus 27. Some students prefer that radical notation instead of the fractional power. So here we go. So 0, 91. We know that 91 is the input. And 0, I said that backwards, 91 is the output, 0 is the input. So it goes something like this. We already did the math for 91 minus 27, that's 64. If you don't know this value, then just leave it there. That is totally okay for the value of c. It is a numerical answer that you could substitute into your calculator. Could you simplify it? Sure. Should you know that the cube root of 64 is 4, and so you get c is 12? Yeah, you should know that, but this is 100% acceptable and would receive full credit. All right, now that we've done that, we need to actually find an expression for y equals g of t, which means isolate y. I really don't like this notation, though, because they say y equals. I would rather see this as g equals some function of t. So you see that you're isolating g and you're doing stuff to t, but oh well, College Board doesn't listen to me. So let's get to it. We know that this is 3 times the cube root of g minus 27 equals negative t plus 12. First thing I'll do is get rid of that 3 and try to write a minus sign correctly. There we go. I always like to write this as a fraction, negative 1/3 t plus 4 as opposed to t over 3, but up to you. Don't forget to distribute your division to everything on the right side. To undo a cube, or a cube root, we cube each side. Watch those parentheses if you're doing multiple steps in one. Gives us g minus 27, and don't you dare distribute that cube. We can't do that. Ends up here. Last but not least, we add 27 to the right side, and so we end up like so. If you were feeling very bold, you could also write this as g of t, totally up to you. But then the crazy part is we're not even done here, because they said, now based on this model, please go ahead and tell us the exact temperature of the potato at a time of 3, which means we need to find g of 3. And luckily, because this is a free response, this is really easy. Done. Right? G of 3, we need to go through and substitute 3 into our equation, and then don't evaluate further than that. We've already evaluated. I guess simplify is the right term. I'm not going to simplify. There's no reason to do that. So I think that looks good. All right, last problem. This is one that I created, but I think it's important to discuss. For t between 0 and 50, another model can be used to predict the internal temperature, and so we have this cool differential equation, J. Find an expression for y equals j of t. Well, very, very similar to the one we just did. We're going to need 3 columns here, somewhat equally divided in thirds. Let's get to it. dj dt equals 30 minus j. Right, and now you can kind of see that weirdness I was talking about before. I'm going to divide the 30 minus j to the left side so it can join dj over here. And then I'm going to multiply the dt to the right side, but that's really weird because then when we slip in these integral symbols, you're like, I'm not integrating anything. Don't forget to put in an invisible 1 if you need a placeholder. Okay. Antiderivative time. The right side isn't bad, it's just t plus c. Derivative of t is 1, c is our constant. The left side, ignoring the 30 minus, is just 1 over j, which should invoke feelings of natural log to you. Natural log, don't forget the absolute value, it is mandatory. And then you might think, well, is that the right antiderivative? So I'm just going to quickly check it. I'm going to say if I do d dj of the natural log of 30 minus j, we get 1 over what's inside times the derivative of what's inside. The derivative of 30 is 0, but the derivative of negative j is negative 1. And so is there an extra negative 1 in this problem out here? No, there's not. We need an extra negative to cancel out the derivative of negative j. All right, nothing else to do there. Let's use our initial condition. This time they told us that we have 45, 31. At a time of 45 minutes, the potato's temperature is cooled to 31 degrees. So negative 1 times the natural log, absolute value, 30 minus 31 equals 45 plus c. Negative 1, natural log, and this part's the important one. 30 minus 31 is negative 1. Okay, if that's negative 1, we normally can't do any log of 0 or negative numbers, so this would be a no-no, but luckily we have absolute value. We had to apply absolute value here to actually get an answer, and that will become important in about, a minute or so. Absolute value of negative 1 is positive 1. And as we learned earlier, any log of 1 is 0. 0 minus negative 1 or times negative 1 is 0. And so finishing this off, it looks like c is negative 45. So what does my equation look like right now? I have negative natural log, and then I'm going to leave off the absolute value for a quick second, t minus 45. Because I'm going to isolate j on this last part, we somehow need to remove the absolute value. And the way that we remove the absolute value is just by having an understanding of when we need to use absolute value versus not. Okay, in this case, we did have to use the absolute value, so we can't just change the absolute value to parentheses, because if you substitute 31 in here, it doesn't work. 30 minus 31 gives us a negative value, and that's a no-go for natural logs. So there are always two branches to a natural log. One is just leaving it as a positive, but the question you could ask yourself is, well, if this is negative 1, what could we multiply in front to turn it to a positive 1 by? And the answer is an extra negative. So what we're going to do here is I'm actually going to put an extra negative 1 inside and kind of double group like so. That's a little messy, but two things to notice. If you substitute in 31, 30 minus 31 is negative 1. Negative 1 times negative 1 brings it back to the positive 1 we had before. And second, I'm going to clean that up right now. So negative natural log distributing and rearranging gives us positive j minus 30 equals t minus 45. So what we're essentially doing here is we're choosing the correct branch of natural log so that we don't have to deal, or correct branch of the absolute value, so that we don't have to deal with the negative versus positive issue anymore, and so that we don't have to find some other way to get rid of the absolute value. You also sometimes see this with square roots. When you introduce a square root, you get a plus or a minus. You do need to pick one. How do you know which one to pick? Well, you pick the one that makes your initial condition still work. All right, the rest of the solving isn't too terrible. I'm going to multiply both sides by that negative. We should remember that to undo natural log, we do e to the power of each side. You should probably group that so we can see it's all together. You cannot distribute e to both of these. Gives us j minus 30 equals e to the negative t plus 45. And finishing this off, we're just going to add 30 to the right side. Please, please, please don't skip these questions. There is a lot of work on them. You need to be very comfortable and fluent with finding the solutions to a differential equation. They almost always represent more than half the total points of a free response in a single part of a problem. You don't want to miss that. Thank you so much for tuning in, and I'm excited to keep reviewing with you. We're just going to go back through the important pieces of differential equations and slope fields while you guys are jotting down the 3 important items that you might want to study or remember for this. First, the words find an expression for y equals f of x is the giveaway that you're solving a differential equation. That's usually worth 5 out of 9 points. And it is almost always the last question on the free response. If you see that right at the beginning, you might be misreading it. Like this one down here started with that, but then they asked for a tangent line. So don't do too much work early on. You might just want to skim through the differential equation and see where they say find an expression. There's usually 4 steps to solving. You separate the variables, you integrate each side, use the initial condition to find the value for c, and then isolate y. Oftentimes, you'll need to choose a correct fork or branch of an equation. If you introduce a square root, don't write plus minus in your final answer. It's okay to do it before you do the initial condition. But once you've done the initial condition, then you need to choose the one that still makes your initial condition work. Same thing when you get natural log of the absolute value of the function. Eventually, you'll need to remove the absolute value. And you do that by either putting a positive or negative in front of this function that's right here. Use the initial condition to guide you. This type of problem is usually going to give you a derivative and an initial condition. So if you need to find the slope of a tangent line, you'll probably have to use the initial condition and substitute it into the derivative. Okay? Generally, with the exception of when you have to find the expression, when you have to solve the differential equation, these problems should be pretty quick. If you're doing lots and lots of work on it, you're probably doing too much work. Last but not least, slope fields are pretty easy points. You're only asked to draw slopes that are defined, so if you get an undefined slope like dividing by 0, you probably did something wrong. So thank you again. Keep studying. I'm excited to see your success on the AP exam.